I've got it started now. Okay, so we left off with the ideal gas law. And the ideal gas law is, and I want you to keep in mind, gases don't typically behave this way if we get to extremes in temperature and pressure. This is just a model that we can use to help us kind of predict gas behavior. But we have to understand that gases are real gases, and this so-called ideal gas doesn't really exist. Okay. The video that you're going to watch, the Ed puzzle about kinetic molecular theory, which we'll talk about today, goes into a little bit more detail about this difference between ideal gases and real gases. So we were talking about the ideal gas law, PV equals nRT, and how this is a relatively straightforward type of equation. We just have to make sure that we have all of our units correct, that our pressure has to be in atmospheres, our volume has to be in liters, N, which is our number of moles, so our unit there is mole. R is our ideal gas constant, the 0.0821, and notice the unit there, liter times atmosphere divided by mole Kelvin, and then our temperature has to be in Kelvin. And that's the huge thing here, and really where we see the errors that result in this calculation is not getting all of those units correct. We have to have all of those units correct so that we can cancel them out of our ideal gas constant so that we're left with the unit that we're trying to solve for. So we had worked a couple of problems, and then I had pulled up a problem, and then that's when everything went haywire. So let me pull up the problem where we were, and we will work on that one. Connor, I see that you raised your hand. Did you have a question? Okay, so here was the problem that we left off with. A 5.44 gram sample of argon gas has a pressure of 2.7 atmospheres at a temperature of 100 degrees Celsius. What is its volume? So we can see, looking at this problem, that I am given pressure, okay? I'm given temperature. I'm looking for volume, and then I have this other piece of information, okay? Think, well, grams is not part of my equation. So if I'm looking here, and if I write everything out, PV nRT, I'm told my pressure is 2.7 atmospheres. I'm looking for my volume. I know R because it's a constant. I'm given my temperature, okay, but remember my temperature has to be in Kelvin, so I add 273 to that, which gives me 373 Kelvin. So I have Kelvin, I have atmosphere, I have my ideal gas constant. I don't have moles. I have grams. So how do I convert from moles to grams? Or from grams to moles? Using the molar mass. So if you're given a problem like this where you have a mass and you need mole, don't just throw your hands up in despair, okay? Remember, you can convert from grams to moles using the molar mass. So we go to our periodic table, and what is our molar mass of argon? 39.95 grams. So I'm going to just come over here and I'm going to say I have 5.44 grams and my molar mass is 39.95 grams. So my grams cancel. And I'm going to say 5.44 divided by 39.95, and I get 0.136 moles. Now, we're not concerned with significant figures here. I'm just going to go to 3 decimals. It turns out that that is how many significant figures I had, but I want to not round too prematurely because I want to have a more exact answer. So we're going to go with 0.136 moles. So that's how many moles of argon gas I have. So now I can plug that in. And now I have my pressure in atmospheres. I have my number of moles there. I have my ideal gas constant. I have my temperature in Kelvin. Now I'm ready to solve for volume. Okay, so now I'm ready to plug everything in and solve. So let me erase this here, and then I'll work the problem right here beside it. Okay, so remember we're at PV equals nRT. I'm trying to solve here for volume, so I'm going to divide both sides by pressure. And then I'm going to have then volume by itself, and I'm going to start plugging things in. So my N is 0.136 moles. My R, 0. Oops, hold on. There we go. All right, 0.0821. I'm going to run out of room. Liter times atmosphere times mole Kelvin, and then my temperature. I'm going to run out of room. Let me move this over. Sorry about that. Thought I could squeeze it all in there. Move over here. So volume, there we go. All right, so 0.136 mole. 0.0821 liters times atmosphere over mole times Kelvin times 373 Kelvin for my temperature. I'm going to divide all of that by my pressure, 2.7 atmospheres. So now I can cancel out moles, I can cancel out Kelvin, I can cancel out atmosphere. I'm left with liter, which is my unit for volume, so I know that that's what I've got to have. So now I'm going to do the math. We'll say 0.136 times 0.0821 times 373, and I'm going to divide that by 2.7, and I get a volume of 1.543 liters. Those of you who are working the problem along with me, is my math correct there? Okay, good deal. All right, so let's look at that answer. Let's look at our problem. What would be our answer in significant figures? And you're looking at that and you're saying, okay, well, I've got my mass, which has 3. I've got my pressure, which has 2. And I've got my temperature. And really, if we take that temperature as it is, we have 1 significant digit. So that was probably not an appropriate temperature to give you. What we would do in this instance is we would go with 1. significant digit, because that is technically how many we have. If you put your answer in 2 significant digits or even 3 significant digits, I would not count it wrong. Okay, I would not count off for that. And typically you're not going to have a temperature with just 1 significant digit, and I wasn't thinking when I put that temperature there. So technically, following our rules for significant digits, my volume is 2 liters. But if you put 1.5 liters or even 1.54 liters, I would not count that wrong. Okay. Because sometimes temperature is going to throw us when we look at our significant figures. Okay. So I wanted to work this problem just so you could see that if you're given mass, all you have to do is convert to moles, and then you're able to work the problem. Okay. Another type of scenario that you might have with ideal gases is that you are given your pressure, your volume, and your temperature, and you're asked to find grams. So if we had that type of scenario, and I'm not going to work one of these, but I just to kind of show you what it would be. So in the course of your problem, you're going to be given your pressure, you're going to be given volume, you're going to be given temperature, and of course you know R, okay? And you are asked for mass, okay? So what you're going to do is set up and solve for N, because that's what you're not given, right? So if I divide both sides by RT, then I have N by itself. So I'm going to work my problem. I'm going to solve for N, and then I'll use my molar mass to find grams. Okay, so it's kind of the opposite. If they give you pressure, volume, temperature, and they say, what is the mass of this gas, then you solve for moles, your N, which we know is moles. Okay, and then you use your molar mass to find grams. So don't panic. Okay, don't panic. Make sure your units are correct. Again, your ideal gas constant has all of those units in there for you. So make sure that you can cancel out all of those units except for what it is that you're looking for. Okay. Now, we can, or before I move on, does anybody have any other questions about ideal gases or the ideal gas law? Okay. All right. So we're going to look at another application for the ideal gas law. And I'm going to be at the top of page 413. Looking at gas densities and molar mass. So again, looking at our ideal gas law equation, PV equals nRT, we can rearrange this, okay, to end up with something that looks like this. Okay, so what we did is just rearranged, okay, and we ended up with this. So we've got our number of moles divided by volume equals pressure divided by our ideal gas constant times temperature. Well, keep in mind, I'm going to put another equation up here. D equals M over V. And we looked at this way back at the beginning of this semester. This is density. Density is equal to mass over volume. Well, over here with our ideal gas equation, how we've restated this, we have moles divided by volume. Well, we can get rid of that by multiplying by our molar mass. Okay, so if we say N over V, that's the same as mole over liter, right? Because our unit for N is moles and our unit for volume is liter. And we multiply that by our molar mass, which is grams per mole, right? Then we're left with grams per liter, which is basically the equation for density. But what we do to one side, we have to do to the other, okay? So we can say then that density is equal to our N times our molar mass, which is kind of this cursive M, divided by volume, which would then equal our pressure times our molar mass divided by RT. So density is equal to the pressure times the molar mass divided by our ideal gas constant times temperature. And why would we do that? Why would we look at that? Well, this tells us, if we're looking at this equation, that our density is dependent upon its pressure, its molar mass, and its temperature. The higher the molar mass and temperature, the higher the molar mass and pressure, the denser the gas. The higher the temperature, the less dense the gas. And when we talked earlier about gases, we talked about how they formed homogeneous mixtures. But a less dense gas will lie above a denser gas. Okay. And your book gives the example of a fire extinguisher. That when we have a carbon dioxide fire extinguisher, when we spray that on our fire, basically what happens is that carbon dioxide is more dense than air. So what it does is it forms a layer between the fire and oxygen. Remember, oxygen is needed for a fire. If you don't get your fire enough oxygen, then it goes out. So when we use a fire extinguisher, what happens is that carbon dioxide basically forms a coating or a covering over the fire that prevents oxygen from reaching it. And it's able to do that because carbon dioxide is more dense than the oxygen in the air. Okay. When we have equal molar masses of two gases at the same pressure but different temperature, the hotter gas is going to be less dense, and so it rises. And that's the idea of the whole hot air rises. And you can experience this. For instance, I live in a 2-story home. So in the summertime, when I go up the stairs, at the top of the stairs, the air is always hotter than it is at the bottom of the stairs. And that's because the hot air is less dense, okay? Going back to this equation, because of temperature, because the temperature is higher, then it's going to be less dense. And so the hot air, the hotter gas, is going to rise. So we can be given these pieces of information and actually calculate our density. So if we don't have our mass, if we don't have our volume, we can still calculate our density. So let's look at this. So this is sample exercise 10.7 on page 413. They ask for the density of carbon tetrachloride when we have a pressure of 714 torr, and a temperature of 125 degrees Celsius. And we've just learned, or we've just kind of reworked our formula to know that density is equal to pressure times molar mass divided by RT. Okay. So our pressure that we're given is 714 torr. Is that the unit that I need for pressure? No, we need ATM. So I've got to convert between ATM and torr. Okay, so I'm going to get my cheat sheet, and I'm going to know that 760 torr is equal to 1 ATM. So I'm going to say 714 torr times 1 ATM over 760 torr. My torr cancels, and I get 714 divided by 760.939 atmospheres. Okay. So now I have my pressure in atmosphere. Okay. What about my temperature? Can I leave it in degrees Celsius? No. What do I need? And how do I get there? Kelvin, right? So how do I get from Celsius to Kelvin? What do I have to do to that temperature? Yes, good. Add 273. So I'm going to take my temperature in degrees Celsius. And I'm going to add 273. And I get 398. Okay, so I have pressure now, and it's in my correct unit. I have temperature in my correct unit. I have my ideal gas constant. I know what that is. Okay. What about this? My molar mass. How am I going to find that? How do I find molar mass? I look at the periodic table, so I have to look at my gas. They told me it was carbon tetrachloride. So you're going to have to put your naming skills to work and know that carbon tetrachloride is CCl4. So what is my molar mass of carbon? Y'all should have this one memorized by now. Yeah, 12.01. What about chloride? Or chlorine? What is my molar mass for chlorine? .45, and how many of those do I have? I have 4. So y'all do the math. What is my molar mass for carbon tetrachloride? Yes, 153.81. So I have my molar mass is 153.81, and that's in grams. And remember, a lot of times when we're looking at molar mass, we just slap that grams on there. But remember, it is grams per mole, and that's going to be very important. We're going to have to make sure that we include that unit there of grams per mole so that we can get the units that we need to cancel out. So just remember that when you're working this, that it is grams per mole. So I'm going to plug this into my equation over here. My pressure, 0.939 atmospheres. My molar mass, 153.81 grams per mole. I divide that by my ideal gas constant, 0.0821 liter times atmosphere divided by mole times Kelvin. And then my temperature, oops, 398 Kelvin. All right, so I want you to see what's going to happen with our units here, okay? Let me change colors so you can see this. All right. So atmosphere is going to cancel because I have atmosphere on top, atmosphere on bottom. Okay. Kelvin, it's going to cancel. Moles are going to cancel. And we are left with grams on the top and liters on the bottom, which is our unit for density. So that is why when we plug all of this in together, we have to make sure we put grams per mole so that our moles cancel out here, because we want our units left to be grams per liter. So that's the important thing there, okay? So we are going to do our math here. Okay. And let's see. I got 4.42. So my density, 4.42. And I'm going to leave it in 3 significant digits because of the numbers that I was given in my problem. And my unit here is going to be grams per liter. Okay. Now, the other application that we can have with this is we can rearrange to solve for molar mass. Okay, so we can also use this to identify molar mass. So that equation would be a little cursive M here. Our molar mass is equal to density times our constant R times temperature divided by pressure. And I just manipulated my equation there to end up with this. So, okay, what we can do with this is we can determine, if we know these other things, we can determine our molar mass of a gas, which can help us identify what gas we're talking about. Okay. So sample exercise 10.8 looks at this on page 414. And I'm not going to work it, but I just want to kind of go through it with you. A large evacuated flask initially has a mass of 134.567 grams. When the flask is filled with the gas of unknown molar mass to a pressure of 735 torr at 31 degrees Celsius, its mass now is 137.456 grams. When it's evacuated again or emptied, okay, and then filled with water, its mass is 1067.9 grams. And they give us the density of water. Assuming the ideal gas equation applies, calculate the molar mass of the gas. Okay. So we're solving for molar mass. Okay. We know R. A little extra hump there in my M. There we go. Okay. Mole times Kelvin. Our temperature, they've told us, is 31 degrees Celsius. And we know we have to add 273 to get to Kelvin. So what does that give me? 304 Kelvin. Okay, so I've got 304 Kelvin. And then they tell me my pressure is 735 torr. And so I have to convert that. And I get 0.967 atmospheres. So I have R, I have T, I have P. I got to figure out density because they didn't actually give us the density of our gas, really. So if you look at the solution, as they talk about it here, the gas volume equals the volume of water that the flask can hold, calculated from the mass and density of water. Okay, and so the mass of water is the difference between the masses of the full and evacuated flask, because they tell us the evacuated flask or the empty flask has a mass of 134.567, and when it's filled with water, it has a mass of 1067.9. So we subtract that out, and we get 933.3 grams of water. So that's our mass of water, okay? And then we rework our density equation. They gave us our density of water. We end up with the volume of the flask being 0.936 liters, okay? Then we get our mass of our gas the same way. We take the full minus the empty. We have our mass of the gas. And now we know the volume because we've been able to extrapolate that from how much water we're able to put in it. So the density of our gas is 3.09 grams per liter. So what makes this problem hard, okay, is getting to the density. So you have to look at the pieces of information that they've given you, okay? You know that density is grams per liter, okay, because it's mass divided by volume, so it's going to be grams per liter. They didn't tell you the density of your gas, but they told you the mass of an empty flask versus the mass of it being full. So you can determine the mass of your gas. They don't give you the volume of your flask, but they tell you some information about water. When they threw that density, the density of water at this temperature, when they threw that in, you're going to have to use that information, okay? So you can use the density of water equation to determine the volume of your flask, and that's going to allow you to determine your density, okay? And then we're going to plug this all in. And I'll run out of room again, of course. R times, I'm just going to put it here, times temperature, and then divide that all by my pressure, 0.967 atmosphere. And again, what we're going to see here is that atmospheres is going to cancel, Kelvin is going to cancel, liters is going to cancel, and I'm left with grams per mole, which is my molar mass. So I'm going to be given a molar mass, and it's going to be in grams per mole. And if we look at how they worked this, it ends up being 79.7. This is your hard part. So if you see a problem like this, don't give up. Think about what it's going to take to get to that density, okay? Now, that was kind of the hard part, reworking this ideal gas equation to get to some different equations. The next thing we're going to look at is another law, so I want you to add this to your cheat sheet. Okay, so go to where you have your cheat sheet. And we're going to have Dalton's law of partial pressures. Now, this is the same Dalton that we looked at way back at the beginning of the semester when we were talking about the structure of the atom. Okay, this is the same John Dalton. He came up with his law of partial pressures, which says that the total pressure a mixture of gases equals the sum of the pressures that each would exert if it was present alone. Okay, so the total pressure of a mixture of gases equals the sum of the pressures that each would exert if it were present alone. In other words, okay, we take the pressures of each individual gas in the mixture, we add those up, and that gives us the pressure of the total mixture of gases. So the equation looks something like this, where P total, so P subtotal, is equal to P sub 1 plus P sub 2 plus P sub 3 plus ... how many ever gases we have. So all we have to do is add up the pressures of each individual gas to give us our total pressure. So that's Dalton's law of partial pressure. Okay. Basically, what it's saying is that each gas really kind of behaves independently of one another. And we can determine that by looking, and this is at the top of page 416, that if we kind of break this down and plug in our ideal gas equation, that all of the gases in the container have to occupy the same volume, they've got to come to the same temperature, and so basically our R and our V and our T become moot, essentially, so that we can add up our pressures. Okay. All right. If we look at a problem, and this is going to be sample exercise 10.10, on page 416, a mixture of 6 grams of oxygen gas, so 6.00 grams of oxygen gas, and 9.00 grams of methane gas, CH4, are placed in a 15.0 liter vessel at 0 degrees Celsius. What is the partial pressure of each gas? So we want to know P1 and P2, so our partial pressure of each gas. And we can write this by replacing our 1 and our 2 here by our gases. So we could say P of O2 and P of CH4. And then what is the total pressure? So they want to know the total pressure. So we've got to figure out our partial pressures, right? And then we can figure out our total pressure. Well, they've given us grams, and we know we can convert between grams and moles. They've given us volume, they've given us temperature. I'm going to go ahead and put that in Kelvin. Oops. Which would be 273 Kelvin. And so what I've got to do first is figure out what is the pressure of my oxygen. And in order to do that, I have to figure out how many moles do I have. So I'm going to start with oxygen. Okay. And so the first thing I've got to do is figure out how many moles of oxygen I have. Oops. So I've got 6.02, or I've got 6.00 grams of O2. And I know my molar mass of oxygen is 16, and I've got 2 of those because it's O2. So I'm going to say 6 divided by 32, and that gives me 0.188, my grams cancel, moles of O2. Okay, and I'm going to do the same thing for my methane. Let's see, I know hydrogen is 1.01 and I have 4. I'm going to add carbon, 12.01 to that. I get 16.05. in 1 mole. And when I divide 9 divided by 16.05, I get 0.561 mole of CH4. So now I've got moles. So now I have moles, I have liter, I have Kelvin, and I can solve for pressure. Okay, so I'm going to use my ideal gas equation. PV equals nRT, dividing here by volume so that I can get pressure. And the first one I'm going to do is oxygen. So P of O2 equals 0.188 moles. My ideal gas constant, 0.0821 liter times atmosphere divided by mole times Kelvin. And my temperature I figured out over here was 273 K. Now divide by volume, and they told me in the problem that was 15.0 liters. So my moles cancel, my liters cancel, my Kelvin cancel, I'm left with atmospheres. Okay. And when I do the math, my partial pressure of O2 is equal to 0.281 atmospheres. So I've got my first answer. Okay, I've solved for my pressure of oxygen. Okay, I'm going to do the same thing for CH4. Okay, so I'm going to rework the whole problem and I'm going to solve for CH4. Since I'm running out of room, I'm just going to do it in my same little spot here and just replace my numbers. But of course you would work this out separately. So my partial pressure of my methane, I'm going to plug in my 561 moles here and then do the math. And I get, for my partial pressure of CH4, 0.838 atmospheres. So now I've got my partial pressure of CH4. So my partial pressure of each one I've got. So to get my total pressure, I'm going to add those up. And I get 1.12 atmospheres. 1.12 atmospheres. So at first this looked really tricky. You're given masses and you're asked to find these partial pressures and your overall pressure. So remember, we can't plug masses directly into our ideal gas equation. We first have to find moles, and that's what we did. We used our masses to find the moles of each one, used our moles to find our partial pressure of each one, and then using Dalton's law, we just added the partial pressure of oxygen with the partial pressure of methane, and that gives us our total pressure. Okay. Okay. Now, let's look at let's look at the kinetic molecular theory on page 418. Okay. So the kinetic molecular theory, and specifically the kinetic molecular theory of gases, okay, or the KMT, really kind of looked at why gases behave the way they do. So the ideal gas law looks at how they behave, but the kinetic molecular theory kind of explains why gases behave the way they do. And I want you to keep in mind, this is a model, of gases. Okay, this is a model. And this is what it says, basically. Okay, that gas molecules are in constant random motion. Okay, they have more energy than solids or liquids, we know that. So they're in constant random motion. So they're always moving. So these little molecules or atoms are always moving. They're just floating around, constantly moving. Okay. So constant random motion. The second thing that this looks at is the combined volume of all of the gas molecules is negligible compared with the total volume in which the gas is contained. So let me explain what that means. So we know gases expand to fill their container. We talked about that last time. That whether we're talking about a box that's the size of your hand, or we're talking about an entire building, that gases expand. So if we have this tiny little amount of gases, it can fill the entire container. So what we're saying here, number 2, is that the combined volumes of all of those different gas molecules is really negligible compared with the total volume in which it's contained. So for instance, you may have a liter of gas, but you put that in a room that has a total volume of 1 million liters. Well, we say gases expand, and so now we're going to say, oh, we have 1 million liters of gas. But if you really get down to the nitty-gritty about it, you still only have 1 liter of gases. So the combined volumes of all of those gas molecules that are in there is negligible compared with the total volume of the container. Okay, so we have to just remember that, and again, this is a model, right? The other thing is that attractive and repulsive forces between the gases are negligible. In other words, they're not going to be attracted or repulsed by each other. Now, we know that's not completely the case. We know that there is some force of attraction between different types of molecules, just like there's force of repulsion. But for our model, and to explain why gases behave the way they do, we just pretend that those forces are not there. So we say that they're negligible, okay? So the gases aren't going to be attracted to one another or repulsed by one another. And the fourth thing is that energy can be transferred between molecules during collisions. But as long as temperature is constant, the average kinetic energy does not change. In other words, as long as we've got a constant system, energy is going to be transferred, but we're not gaining or losing energy in our system. We're going to keep the same amount of energy in our system. So we can essentially pretend that this is an isolated system, right? Like we learned from the last chapter. So what does all of this mean? What does it mean in plain language? Well, basically what it means is that gases are in constant random motion. And as they are in motion, they bump into one another. They collide. And they can exchange energy during this collision, but it doesn't change the overall energy of our system. That they're going to collide with each other. They're going to collide with the walls of the container, but we're not going to add any energy or take away any energy to the system. And so the fifth thing is that the average, and I've kind of already alluded to this, kinetic energy is proportional to absolute temperature. And we say absolute temperature here, we're talking about temperature in Kelvin. And so at any given temperature, the molecules of all gases have the same average kinetic energy. So what does this mean? Well, pressure. It all comes back to pressure. And it really explains the relationship between pressure and temperature and the movement of the gases. The more collisions that the gases have with one another and with the sides of the container, the more pressure that is going to be exerted upon the container or the walls of the container. So I do this little activity in Intro Chem, and those of you that were in Intro Chem will remember this from last semester. I took a rope and we made a square with a rope, and we put people inside the little square, and each person served as a gas molecule. And so they were in constant random motion. And as they moved, so basically they're just walking back and forth, and they bump into each other, and they bump into the rope, the sides of the container. Yeah, the mosh pit. Yeah. And so when our temperature was lower, meaning our molecules weren't moving as quickly, then there were less collisions. They didn't collide with each other as much, and they didn't collide with the sides, the walls, the rope as much. And when we slowed down when we decreased the temperature, which meant we slowed down the movement, then there were even fewer collisions, which further decreased the pressure. But when we added temperature, in other words, now the molecules are moving faster, like Miguel alluded to, it did kind of become a mosh pit. That as the gas molecules, as our students were moving faster and faster, then they bumped into each other more. They bumped into the sides of the container, our walls, more. And so it created a really high pressure situation. So gases behave the way they do because they are in constant random motion. Because they all contain kinetic energy. Because they're in motion, they have energy of motion, which is our kinetic energy. And that there is a direct relationship between our temperature and our average kinetic energy. As we increase the temperature, we increase kinetic energy. And as we increase kinetic energy, we increase the movement of the gas. So there's going to be more collisions with each other and more collisions with the sides of the container, the walls of the container. And so we get to a high pressure situation. And so that's why gases behave the way they do. Molecular motion increases with increasing temperature, and that in turn increases our pressure. Okay, so that is our kinetic molecular theory. And so then we can apply that, and we come up with two things in which we can apply this. Oops. One, an increase in volume at constant temperature causes pressure to decrease. And then number 2, leave some space if you're taking notes here. A temperature increase at constant volume causes pressure to increase. Okay. So an increase in volume at constant temperature causes our pressure to decrease. That's Boyle's law, right? So this kinetic molecular theory is what explains Boyle's law. If we're at a constant temperature, so if we're at a constant temperature, the average kinetic energy remains unchanged, right? Because that's what pumps kinetic energy into the system, is if we change the temperature. But if we keep the temperature constant, if it remains unchanged, then our average kinetic energy of our gas molecules also remains unchanged. And so when we increase volume, the molecules have to move further or have to move more to have collisions. So the molecules have to move a longer distance to achieve collisions. They're not as close to one another anymore when we increase the volume. Okay? So if we increase volume, even though our speed has not changed, our pressure decreases because now our gas molecules have to move further. And we saw this in our little mosh pit example, that when we made the rope area larger, we had less collisions. And when you have less collisions, you have less pressure. Okay? So this means we have fewer collisions. So this explains Boyle's law. Okay? But if we look at the second one here, an increase in temperature at a constant volume causes pressure to increase. This means now that our average kinetic energy has increased because we've increased temperature. So now our gas molecules have more energy. So now they're moving faster. And if they're moving faster, there are more collisions between the molecules and more collisions with the wall. So because we're not increasing the size of our container, we increase pressure. And that's exactly what happened in our mosh pit example. That when we increase temperature, and for our purposes, an increased temperature meant that now instead of just walking, our people were almost running. They were walking very quickly. And so as they were walking very quickly, they were bumping into each other and into the sides of the container much more often. So it increased the pressure in the system because there were more collisions. Okay, so basically our kinetic molecular theory of gases can explain the gas laws as we know them. Okay, that's what explains the gas laws. So we take the gas laws at face value. Okay, like yes, P1 V1 equals P2 V2. I know that as we increase volume, we decrease pressure. As we decrease volume, we increase pressure. But why? Well, this is why. Okay. We increase temperature, we increase pressure. Why? This is why. Okay, so it all has to do with the kinetic molecular theory, that the idea that the gases are in constant motion. And if we increase kinetic energy, then we increase their motion. If we decrease kinetic energy, we decrease their motion. Okay, so that's the kinetic molecular theory. It really just explains kind of the heart of the matter with our gas laws. Okay. On page 423, you have a couple of different definitions that I just want to hit on. And those are effusion and diffusion. Okay, effusion and diffusion. Effusion is the escape of gas molecules through a tiny hole. And diffusion is the spread, and we're going to, now this can be the spread of any substance, but I'm going to use it in terms of gases because that's what we're going to talk about. But this is the spread of a gas throughout a space or another substance. Okay. And the effusion rate, you've got Graham's law of effusion. We're not going to do anything with this, but Graham's law actually states that the effusion rate of a gas is inversely proportional to the square root of its molar mass. In other words, there's a relationship between the effusion rate and the molar mass of the gas. But what does this mean for us? Okay, so let me give you an example of effusion and diffusion. So a Coke. Okay, so we know that a Coke is fizzy, right? So what makes a Coke fizzy? Somebody tell me. Carbon dioxide. All right, so we have the Coke, right? That's liquid. And then we have carbon dioxide gas. Yes, the carbonation. That's the carbon dioxide gas that is dissolved within it. Okay, so that's essentially diffusion. That we've pumped in this carbon dioxide gas to our liquid. It has spread throughout that substance. It is spread throughout the liquid portion of the Coke. So if you have a can of Coke, okay, then you have a situation where carbon dioxide is diffused throughout the liquid. Okay, that's diffusion. If you open that Coke, and we're going to open it real slowly. Okay, we're going to open it really slowly. So we open that Coke, and whether it's a bottle or whether it's a can, what happens as you start to open that Coke? It fizzes, right? We get that fizzing sound. We can hear that gas. That's effusion. Okay, that now we have broken that seal, and we're now allowing some of that gas to escape through a tiny space. So that fizzing sound that we're hearing is essentially effusion. That is the escape of those gas molecules. We can't keep them all dissolved in that solution. Okay, they are going to escape. And if we open our Coke, and as we open it just a tiny bit, we start getting the escape of those gas molecules through the hole. Now, what happens if you have, let's say, a bottle, let's say it's a 2-liter Coke, and you have that and you drink it, and then you put the lid back on and you stick it in the refrigerator, and then you forget that you have that Coke in there. What happens? It goes flat. So what does that mean? When we say that it gets flat, what does that mean in terms of the gases here? What's happened to the CO2? Exactly. The gas is no longer dissolved in the liquid. It has diffused out of the liquid, okay, into the space in the bottle. And because we can't get a perfect seal on it anymore, it effuses out of the bottle. And so we get to the point now where the only thing that's left is the liquid. We have no more carbonation. Okay, so a bottle of Coke really almost perfectly demonstrates these two topics, that the gases are dissolved in the solution, so they're diffused essentially in the solution, and when we open that bottle of Coke, the gas molecules start to escape. They're the ones that aren't dissolved, or as they diffuse out of the solution, they start to escape. And if we leave it open long enough, or if we don't perfectly seal it again, then we come back to our Coke and it's flat. And it's because all of the carbon dioxide has become out of solution. It's not dissolved in the liquid anymore, and it has escaped. It's diffused out, and it's left the bottle and diffused into the environment. Okay, so that's the difference between effusion and diffusion. And we're not really going to talk about anything other than that. The last thing I want to briefly mention is about real gases. Okay, that everything we've looked at thus far in terms of this ideal gas law and these ideal gases, we were looking at an ideal gas, really a gas that doesn't exist, that an ideal gas behaves the same way under all conditions. And we've learned enough now about gases to know that we can't get our gases to behave the same way in every circumstance. In high pressure, high temperature, high or low pressure, low temperature, we can't get our gases to behave the exact same way every time. So an ideal gas is a model. It doesn't exist, okay? So a real gas, and if we look at page 426, there's a little bit about this, that a real gas does not behave ideally at high pressure, okay? And so they can't behave like, real gases can't behave like ideal gases at high pressure. And also the deviation increases as temperature decreases. Okay, so if we have a high pressure or a low temperature situation, then our gases do not behave ideally. Okay, so again, gases do not behave ideally, and when I say that here, I'm talking about in relation to the ideal gas law, at high pressure and low temperatures. In other words, if we have a really high pressure or a really low temperature, we can't use the ideal gas law, because our gases at that point are not behaving as ideal gases. Okay. And there are also going to be attraction forces. So in reality, there are attractive forces. What I did there. Attractive forces between gas molecules. Okay, so there are attractive forces. Remember we said that we just disregard that we pretend that there aren't. Well, there are. Okay, there are forces of attraction. And that is summed up with what we call the van der Waals equation. We're not going to get into it. We're not going to do anything with it. But we can measure the forces of attraction using the van der Waals equation. So gases don't behave ideally when we get to a high pressure or low temperature situation. And we do have to consider that there are some attractive forces. Some of them are quite low, but there are attractive forces at work. And so the gas molecules will be attracted somewhat to one another or repelled by one another. And that's why when we look at the ideal gas law and we look at the kinetic molecular theory, we have to use these as models. It's not the end-all be-all. We just use them to help us visualize how gases behave, because there's no such thing as a true ideal gas. But we can almost achieve that within certain conditions. And when we do that, then we can really look at the behavior of gas molecules, how they behave, and why they behave the way they do. Okay. Well, that's all I have for you. Do you have any questions? Yes, Xavier, question. You can type it in the chat box if you want. Oh, the group assignment. The group assignment for thermochemistry, that was due last week. What are you wondering about it? Like what specific thing?
Can you hear me? Because I didn't want to type the thing.
Yeah, I can hear you.
Okay, well, when we first got the information about it, I like tried to text everybody in my group on what to do, and I think it wasn't much of communication, because we have the paper and everything, but I don't entirely know what's going on. I wasn't filled out or assigned to anything at all, and I wondered if anybody in my group had turned in anything.
What group were you in?
Group 1.
Group 1. It looks like some of your group turned some things in. Let me take a look. Okay. Yeah, it looks like, yes, it looks like your group did turn in something.
I don't entirely know what all I should turn in, because like I said, nobody assigned me to anything. I asked around, nobody answered or gave me anything to do. So what should I do exactly?
Let me, when we get off this call, our collaborate session, I will send a